Thank you. It's a real pleasure to be here. And given my background is, even though PhD in atomic physics, I've really spent most of my time in particle physics and 20 years thinking about X-rays. I feel like I'd like to start, when I talk about the X-ray laser at SLAC, by just a few words on why X-rays are interesting and why they're important tools for science. And the first important thing about X-rays you all know, which is that X-rays penetrate. And you all know that because if you fall off your bike and hurt your arm, you go to the doctor X-rays your arm to see the bone inside. And this is my favorite X-ray, which is an X-ray of my son when he was about 8 years old, and he had swallowed a quarter. And we had to go up to the emergency room up at Cayuga Medical Center. I was in Cornell at the time. They wanted to make sure the quarter had made it safely to his stomach. And you can see his nice straight spine, pelvis, ribs, and the quarter. It's actually a great X-ray. The focus of the X-ray is right at the quarter, and you can make out George Washington's profile in the original. Okay, so X-rays help us see through matter. But they do other important things because of the very short wavelength of X-rays. We can use X-rays to tell us where atoms are in materials, and we can even use X-rays to probe where electrons are in materials and what the electronic properties are of materials, which can be very, very useful in device development. Now, we've used X-rays to determine structure at the atomic level for decades. This is not a new tool, and over the past several decades, accelerator-based X-ray sources, synchrotrons, have become workhorses for many, many, many fields in material science and chemistry and physics. And I've just given 3 examples here of what some of the science that's come out of studies with X-rays. A very nice example was the Army had some night vision goggles. They were using them in the Gulf. And in the very hot, dry atmosphere of the Gulf, the coatings on the night vision goggles were deteriorating very rapidly. And so they sent them to one of the X-ray sources where they studied the structure of the film on the surface of the goggles, understood the reason it was deteriorating it, reinvented it, and made, actually not only solved the problem of the aging of the night vision goggles, but were able to improve their efficiency by a fairly significant factor. Very practical use of X-rays. Another use was to develop a treatment that blocked a mutant enzyme used as a therapy for stage 4 melanoma. Not a cure, but was extending the life of patients by up to 6 months. And then the structural basis for immunity to H1N1 flu was also determined, tool used for decades. But there's a new frontier. These are essentially static studies of structure using X-rays. The new frontier is time. Okay? What's going on very, very fast timescales in the atomic world? So to see how important time information is, I'm going to use a really classic example. Back in the late 1800s, there was a big question of how does a horse gallop? Okay, your eye is not fast enough to process what the horse's legs are doing, and so it sort of looks like a blur. And if you look at pictures of how horses galloped before the late 1880s, you see all sorts of imaginative ways that horses were depicted as galloping. And that all changed when a very clever guy was able to take a moving picture of a horse. It was actually the result of a bet. This is a very Stanford story. Senator Stanford had a lot of horses, and he was very interested in this question of how does a horse gallop. So he made a bet, and a very clever photographer named Edward Murbridge developed a camera with a shutter speed of 0.001 seconds, okay, the fastest shutter speed in the West. And he set up a series of tripwires and took a series of stop-action pictures. You can actually see the numbers of the on the stop-action pictures, and then he put them together into this motion picture, and you can immediately see how the horse gallops. All 4 feet, pardon? This is galloping. All 4 feet are leaving the ground, and they are leaving the ground when the horse is when the legs are under the horse's belly. So this is an analogy to what I am now going to talk about in the X-ray world, imagine what would happen if you had an X-ray camera. So you've got the ability to penetrate material, see things at the atomic scale. But imagine it had a shutter speed, or the effective shutter speed, of 0.000000000000010 seconds. That's 10 femtoseconds. If you had such a camera, using the analog of the galloping horse, you can imagine taking a series of stop-action pictures of chemistry in motion, because femtoseconds is the time scale that chemistry happens. You would see electrons and atoms moving on their natural time scale, and you would see chemical reactions atom by atom. That is the new frontier that I'm going to be talking about with X-rays and the development of the X-ray laser. This is the new frontier that was opened in 2009 when we turned on the electron laser at Stanford. So, you might be able to do with such a source. You can imagine movies of chemistry in action. One example I'll talk about at the end of my talk is to study the time structure, the dynamics of the photosynthetic process, which, after all, is pretty important in life on our planet. You can study structure and time-resolved function of perhaps someday single molecules, proteins. So we've been able to do static structure of biologically interesting materials. We can now start to study dynamics. You might be able to do 3D imaging at the cell level, and you can characterize transient states of matter in extreme environments and study those as well. So that's just sort of an overview of why this is an interesting topic and what one might do if one had such a tool. So the way I'm going to proceed with my talk is I'm going to tell you a few basics about what an X-ray free electron laser is, how does it work. It's the specific kind of free electron laser I'm going to be talking about is called a SOSI, self-amplified spontaneous emission free electron laser. I'll tell you about the first hard X-ray version of this that we turned on at SLAC, something about the early performance, and then the first experiments. And I'll end, if I have a few minutes at the end, with what's to come, because this is a burgeoning field, and there's a lot on the horizon. So the first thing I have to say when I talk about the LCLS is that a free electron laser it's actually not a laser. Okay, a laser, if you remember what the acronym stands for, is light amplification by stimulated emission of radiation. That's not what's going on in the free electron laser. However, the product of the free electron laser is intense, coherent radiation. And so on the sort of theory that if it walks like a duck and it quacks like a duck, we're going to call it a duck, we're going to call this a laser. The free electron laser is not a new invention. It was first pioneered by a very interesting gentleman, John Mady. In 1977, he operated the first free electron laser at Stanford, and it was in the infrared. And to date, there are literally dozens of free electron lasers in the infrared and the visible around the world. And there's one in the soft ultra in Germany, which was really a pioneering, very important step to the development of the first hard X-ray free electron laser. The concept of a hard X-ray free electron laser was introduced in 1992. As you might imagine, as the wavelength gets shorter and shorter, these things become more and more difficult to build because the tolerances scale at least with the wavelength and probably as some high power of the wavelength. Claudio Pellegrini invented the concept of the X-ray free electron laser. He recognized that with a powerful electron accelerator, and we just happen to have one at SLAC, one could possibly make a hard X-ray free electron laser. And and then the DOE to buy on to this, but by the early 2000s, this became a construction project at SLAC. We already had the electron accelerator, so this only cost $400 million plus another $100 million for the instrumentation. In Hamburg, where they had to build the whole thing from scratch because they didn't have an existing electron accelerator, it's well above $1 billion. So these aren't going to be on everybody's lab bench anytime soon, but they are tremendous tools. The concept of how it works, so imagine an undulator magnet. Undulators are familiar from storage rings. It's just a magnet where it has alternating poles, up, down, and so if you send a bunch of electrons through, the electrons wiggle. They feel that magnetic field as they're moving along at relativistic speeds. They wiggle or undulate going down the magnet, and when you take an electron and you accelerate it, it radiates. That's a technique that's been used for a very long time. But if you start with a very, very short bunch of electrons, and I'll define what that means, a very intense short bunch of electrons that's going to typically be of micron dimensions, and it's going to be typically billions of electrons, and you make this undulator magnet very long, and by very long, I'm talking like 100 meters long, then what starts to happen in the very intense field generated, radiation field that the electrons start to generate, it's incoherent at first, but the incoherent radiation from the back of the bunch starts to create order in the bunch. You have a process called microbunching. And the electron bunch breaks up into a series of little micro bunches, each separated by roughly a wavelength of the radiation, characteristic radiation. And those microbunches are ordered, and they start to radiate coherently. This is all classical or relativistic electrodynamics. There's not, there's no stimulated emission necessarily going on here. This is an electromagnetic simulation of a bunch of electrons in an undulator magnet, so they're being accelerated in the undulator magnet, and you can see the microbunching start to evolve in the electron bunch. And this is, period here is about a wavelength. That's the characteristic wavelength of the radiation. So just slightly more technically, if you want to, at the beginning of the undulator, you have a lot of spikes of radiation. The microbunching starts to occur, and some of those spikes win over others. And at the end, it's fully saturated. You have exponential gain, ultimately saturation. And a typical free electron laser pulse of 100 femtoseconds or 200 femtoseconds will have something like 10 to the 12th photons in 200, 100, maybe even 50 femtoseconds. And that'll be a few hundred coherent spikes. This doesn't actually, the output does not look like your normal laser, where you would love to have just a single mode. It's a lot of these coherent spikes incoherently related. And obviously, single mode operation is something that we would like to get. And that to do that, you need a strategy to seed the pulse, because this process I've just described is essentially amplifying noise. Okay? The electron beam is absolutely key to the free electron laser success. In fact, the way that John Galida, who was the project manager, project director who built this, said for years, and I didn't understand what he meant until we finally turned the thing on, it's all about the electrons. If you can get the electron bunch right, low emittance, small, high peak current, if you can get that electron bunch right, you will laser. What that means is you have typically 6 billion electrons in a spatial volume characterized by roughly a 30-micron sphere. That's an incredibly high density of electrons in a bunch that you're going to send down your accelerator. And this is an image just of what the bunch looks like at the end of the limit. That turned out to be good for SLAC, because making specialized beams of electrons is something we've been doing for about 50 years. So the name of the X-ray laser at SLAC is the Illuminating coherent light source. This is a picture of the SLAC site. If you've been to Stanford or been to the Bay Area, San Francisco's up here somewhere. The Pacific Ocean's over here. San Andreas Fault is over here. The main Stanford campus is about 2 miles down the road. And existing at SLAC, since it was built, is a 2-mile-long linear accelerator, electron linear accelerator. The LCLS uses the last third of the accelerator. It actually doesn't need the whole accelerator. The goal was to make X-rays between 800 eV and 8 kilovolts. And for that, we were going to need electrons up to about 15 GeV, and the 2-mile LINAC makes 50 GeV. So we only needed a third of it. I'll come back to that when I talk about the future and upgrades to come, because since making the first free electron laser was a success, as you might imagine, we're already started on taking another third of the LINAC and doubling the capacity of the machine. So the electron accelerator already existed. We added a transport line, an undulator hall, and then 2 experimental stations. This one's actually underground. And again, for those of you who've been in the Bay Area, Freeway 280 goes right over the LINAC. So this is the basics of how the thing works. You have an injector at the 1/3 from the end, and the injector has a normal that's sent down the 40 feet underground to where the actual LINAC is. You have laser pulses coming down and hitting a cathode, copper cathode, and ejecting bunches of electrons. That's where it starts. They get pre-accelerated and injected into the 50-year-old SLAC LINAC. And then those electrons are accelerated to, depending on the wavelength of the X-rays you want, somewhere between 5 and 15 GeV. After the electrons are accelerated, they go through a drift area to get them through the research yard. That's really mostly for convenience. And then they go into the undulator hall, and that's where the magic happens. We have 100 meters of precisely aligned undulators, and really precisely aligned. We, in fact, use the electron beam to align them. The electrons are wiggled along in the undulator. The microbunching occurs, and the X-rays are generated. So at this point, you've got X-rays and electrons going along collinearly, with a 120 hertz rep rate. At this point, the electrons have done their job, and we get rid of them. There's a large magnet. It bends the electrons down into a dump in the floor, and the X-rays stream free at 120 hertz into the experimental halls. We have 6 experimental stations. By the way, you can immediately see one of the downsides of this machine is it's very linear. Unlike a synchrotron where you can have 30 end stations, we can have 6 experiments. They're all in a line. The beam goes to 1 experiment at a time, which is a real bottleneck. This is what a typical experiment might look like. So this is what it looks like with 100 meters of precision-aligned undulators. This is the actual undulator magnet here. There's 30 undulator magnets, each one 3 meters long. What you're really seeing is mu metal shielding, but these precision stands, this very thick concrete floor, and the temperature-controlled, vibration stabilized because of the high demands on the alignment. Now, we spent 2 years commissioning the last third of the LINAC to develop these beautifully, exquisitely tailored electron bunches. We then installed the 100 meters of vacuum tube through the undulator hall. The beam pipe's about the size of a soda straw. And there was a betting board of how many pulses it would take to get the electron bunch through the soda straw, the 100-meter long soda straw. And the winning bet was 2 shots. And then we moved the undulators onto the beam line. So I have to say at this point, we did not actually know that this was going to work. There were many people in the community, in the X-ray community in particular, who thought that this was $400 million being wasted because you probably would never get the thing to laze because of the demands on the tolerances. Up until this point, free electron lasers had a very well-deserved reputation for being finicky and difficult to operate and cranky. And so we defined what we called the lasing campaign. And that's code for, we thought this was going to take a while, and so we were going to start putting undulators on the beam line and start trying to make the thing laze, but we called it the lasing campaign because we thought it was going to be weeks and maybe months before we could actually deliver radiation. That started about 7 o'clock, and we rolled it individually onto the beam line, aligned it, rolled it off, rolled the next undulator on. That was fine. Everything got aligned. And then the campaign was put undulator number 1 on, number 2, number 3, And at some point, hopefully before you reached undulator 30, you'd start to see this process kick in, and you would actually start to see some lasing radiation. So here they are in the control room. This is Paul Emma, who led the commissioning team. And I visited there about 5 o'clock in the afternoon before they officially started. And the atmosphere was so thick you could cut it with a knife. I mean, the people were really tense. And they're looking kind of worried. This is John Galida, the project director for the construction project. And there they started to see the first lasing spot. And then they were real happy. So I had gone home and gone to bed, because lab directors go to bed early on Friday nights. And at 10 o'clock, I was woken up. 3 hours after they'd started, we have a laser. It just worked. I've been an experimental physicist for a long time. This was just unreal. In fact, we didn't believe we were really seeing lasing for the first week, 2 weeks. You know, we didn't make a big press announcement because we were just afraid something was going to go wrong. But in fact, it was lasing. They closed about 11 o'clock at night. They closed the shutter on the electron beam, so the electron beam wasn't going into the undulators anymore. They came back at 8 o'clock the next morning. They opened the shutter, and it lased. Okay. So, and it's sort of been just doing that ever since. This has been, it's the dream machine. Just to set the scale, if you look at peak brilliance versus energy, this is where the storage rings are. This is where LCLS turned on. With turn on, we were 1 billion times brighter than any source in that energy range. And with a factor of billion, you can do a lot of fun things. The other thing that was just stunning was within weeks, we weren't just meeting design expectation, we were exceeding it. And two of the most important things, it just turned out to be really flexible. We were getting more energy per pulse than we were expecting. The pulse energy turned out to be more flexible than we realized. We've been able to go down in energy of the X-ray energies. But maybe the most important one, which came within weeks of initial turn-on, was the initial spec was 200 femtoseconds for the pulse width. But with a special low charge mode, they were able to go sub 10 femtosecond pulses. Now, I say sub 10 femtosecond because the fact is we don't yet have an ironclad way of measuring the pulse widths below 10 femtoseconds. It's very hard to measure pulse widths that fast. We're working on some techniques. And that's turned out to be really important for getting the science out, as I'll explain shortly. The other thing that I'll just, it's a little technical, but I'm going to spend one slide on, is we've actually been able to also demonstrate self-seeding in the hard X-ray regime, which is extremely important because beautiful as this is, I have to emphasize, we're amplifying noise. There's a lack of control of the exact frequency spectrum. It's a whole series of little spikes. That's unattractive for doing experiments, and being able to improve on that was very, very high priority. So, but the first performance certainly exceeded expectation. This is the gain curve we were able to produce. Actually, the graduate student produced that within the first week. And these are just some of the typical parameters. One of the things that was definitely just a bonus was the emittance turned out to be, of the electron bunches, turned out to be better than we had thought we could get, which meant that we had 100 meters of undulators. We had 30 undulators, but we actually only needed 20 of them to reach saturation, which meant we had 10 undulators to play with, which turned out to be terrific. Now, of course, the DOE did say, well, maybe you over-designed it. Fine. We've taken advantage of that. So let me talk just one or two slides on the self-seeding, and I apologize, this is going to be a bit technical, but I think it's really important. So this is what a pulse, if you look at the spectrum of a pulse out of the LCLS in SOSI mode, this is what it looks like at 9 kilovolts. So it's 20 EV wide, full width. It's about a 0.2% bandwidth, which is not shabby. I mean, that's a great tool in the X-rays, and these individual coherent spikes are coherent. But this is one pulse. The next pulse will have the distribution of those spikes very different. So if you were to put a monochrometer in front of your sample, because these spikes are shifting around. So Okay, so at the beginning, the experimenters were thrilled. They start doing experiments, and then they start complaining. Can't you do something about these noisy spikes? So these three gentlemen from Daisy published a paper, and it was, let's see, if this is 2013, 2012, it was in 2000, about halfway through 2011. So LCLS had been running for almost 2 years. And what they came up with is an incredibly clever idea to self-seed the pulse. Okay, so the idea of a seed is that instead of that you amplify in this amplification process, in this single pass amplifier, which is what this is, right? No mirrors anywhere. And the idea was this: you take the first 10, 15 undulators, and you get the SASE process going, and you make a pulse that kind of looks like this, but has less energy. You then actually take an undulator out, and in the gap, you put in a magnetic chicane to separate the electrons from the X-rays. And with this little chicane, you actually delay the electrons with respect to the X-rays. That's the first very counterintuitive thing I'm going to do, is delay the electrons with respect to the X-rays. The next thing is you put the X-rays through a very special diamond crystal that can only be made at one institute in Russia. How typical. And with that very special diamond crystal, you kick out a very narrow piece of the frequency spectrum of the X-rays. Now, something should be bothering you right now, because I'm going to kick out a narrow piece of the spectrum. What you're expecting me to do is filter out all the junk and keep a narrow piece of the spectrum and then put the electrons on that and use it as the seed. I'm not doing that. I'm kicking out the spectrum so that after this X-ray, after this crystal, the spectrum of X-rays has a notch. Okay? A notch in frequency space produces ringing in the time domain, which is ringing in position. So here's the SASE peak, and here's the ringing I've now induced by taking out a slice of the frequency spectrum. I now arrange my chicane so that the electron pulse comes back, doesn't line up with the main SASE pulse, but lines up with this little ringing tail, which, by the way, is generated by this monochromatic notch, and that's the seed. Okay, so I'm using the notch as my seed, and this is what you get. This is the SASE spectrum without seeding, and now this is what I get with my hard X-ray self-seeding, and it works. Same energy, roughly, in the broadband as I've now put it all into one coherent spike. So we ran the test experiment a year ago. The Daisy guys came out and helped run the experiment. The flexibility of the machine allowed us to actually do this in between user runs, and now we're actually gearing up. I think the first users who will run with a seeded beam will be coming in the next month. So that's a big deal. All right, so I now want to turn to the science. The first science question we had to ask is, actually, I showed you this nice picture of the galloping horse and so forth, but can we take stop-action pictures with an ultra-bright, ultra-short X-ray pulse? I mean, because actually, when you put some little object in this pulse and you hit with 10 to the 12 X-rays and 100, okay, it's not there anymore. So we definitely destroy the sample. And the question is, can you actually get any information out before you destroy it? So we call that technique probe before destroy. And then if you can make this work and prove that it works, can you actually use this to study chemical dynamics? And the example I'm going to use is photosynthesis. So probe before destroy. The idea for this was a seminal paper published in Nature in 2000 when people were really starting to get serious about X-ray lasers. And the concept is, imagine you have an X-ray laser that's giving you pulses at, it could be 120 hertz, it could be a kilohertz, it could be 100 kilohertz. Doesn't really matter. They're coming along, these pulses are coming along, and you imagine you're dropping some kind of particle into the beam so that X-ray pulse intersects particle. What happens? Well, you diffract the X-rays, and you get a diffraction pattern, and you destroy the particle. Okay? So the claim from this paper was that if you could get X-ray pulses short enough, you could get the diffraction before you destroyed the sample. So I have to say this is a little like on each of those images for the galloping horse, we're going to blow the horse up. But before we blow it up, we're going to actually get its, configuration. That's why I had the breaking light bulb picture as the example. So obtain the atomic positions. We have a chance because atoms move rather slow. I mean, the first thing that happens when the X-rays hit the object is that they kick out all the electrons, and then you have a Coulomb explosion. But maybe you can actually record what happens, capture the atomic positions before they start to move. Can we actually measure dynamics this way? And the first step, instead of starting with small particles that were too small, we decided to do something clever, or it was actually other people's idea. I'm not going to take any credit for this at all. The experimentalists decided to do something incredibly clever, which was start with small crystal samples rather than single molecules, because you'll get the enhancement of the Bragg's law will give you an enhancement of the signal, which will be helpful. So one slide on crystallography. Again, people have been taking crystals of biologically interesting materials and sticking them in synchrotrons for decades. That's how the flu virus and the melanoma enzyme were determined. When you go to a synchrotron, you have to grow a reasonably large crystal, and you leave it in the beam for a while, and you rock it back and forth to get different orientations. And the big issue there is you want to grow a big enough crystal that you have enough radiation on the sample to get enough signal to record without damaging the sample, because these are sensitive samples, and the radiation damage changes the configuration, and then you don't learn what you think you're going to learn. And there's been a huge bottleneck with growing large crystals. Some things crystallize easily, some things don't. So the idea here was use the free electron laser where you have incredible intensity. You're going to blow it up anyway, so that's definitely radiation damage, but you can maybe get the image of the structure before you damage it, and you can do it with a tiny crystal, because probably when you're trying to grow big crystals, you're actually flushing little crystals down the sink all the time. And so growing little crystals probably is easier than growing big crystals. And the way that the crystallography works is you start with your crystal, you get a diffraction pattern, you get an electron density map, and then you make an atomic model, and there's a refinement process that goes on. This is extremely well developed after decades of research. So again, just a little video to illustrate this. These are the X-ray laser pulses coming in. You're dropping in your little nanocrystals. Each one gives you a diffraction pattern. Of course, the orientation is independent. Each one has a different orientation, and somehow you have to figure out how to put all those diffraction patterns together, and then from that reconstruct what the original sample looks like. And the analogy I like to use is it's like taking a misshapen rock and dropping it in your swimming pool and using the pattern of the ripples along the side of the pool. And you do that enough times with enough misshapen, you take the same misshapen rock, but you drop it in different orientations. You keep recording those ripples, and eventually you reconstruct the shape of the rock. Okay? But people can do this. And so we tried doing this at LCLS. This is a very early experiment where we actually were just operating with soft X-rays, so we weren't going to get terrific resolution. They had a jet with a flowing water jet, liquid jet, with little nanocrystals in it, and intersect it with the X-ray pulse, and then some CCD detectors, a near detector and a far detector to record the diffraction. This is what the actual original chamber, it came over from Germany. The Germans are building an X-ray free electron laser that should turn on in 2016, 2017, but they started very early in investing in the scientific technology of how you were going to use a free electron laser, and we benefited enormously at SLAC from their investments. So they moved this whole chamber over that had the flowing jet. It's actually, the jet is flowing into the paper here, into the screen. The red is the X-ray laser beam, and then the near detector, silicon detector is here, and the far detector is there. And obviously, the detectors have holes in them because the X-ray laser, if it hits the silicon detector, that's the end of that pixel, or set of pixels. So this is a picture from the far detector, and I really like this picture because I'm sorry, I think maybe you can make it out. The coherence of the X-ray beam is evident. Can you see the fringes? There's fringes, okay? Now, you can not only see the fringes, you can count the fringes. So these are the Bragg spots from the crystalline structure. But remember, this crystal is a little nanocrystal. It's only maybe 14, in this case, you can count it. It's 14 by 9, or excuse me, 16 by 11, because it's n minus 2, unit cells. In this case, it's a known sample. We know the size of the unit cell. So you get the fringes in between, right? This is like multiple slit experiment. And you can actually get the size of the crystal. This is 400 nanometer by 220 nanometer crystal. Okay? But the coherence is just evident. This is now what the near detector shows. Just the wide angle diffraction and the diffraction spots. This is a single shot of a nanometer sized nanocrystal. And these diffraction patterns are clean enough that the standard indexing programs can determine the orientation of each nanocrystal. You can then put them all together and extract with poor resolution, because I only used 1.9 kilovolt X-rays. I can reconstruct the structure of this is photosystem 1 and compare it with conventional data. So this was the first proof of principle with poor resolution, sort of roughly 8 angstrom. I think ultimately they got close to 6 angstrom resolution, that this technique worked. Now you can say, well, wait a minute. Maybe you're really just, I mean, this is poor resolution. How do you know you're not damaging the sample? Obviously, studies were done, theoretical studies on, you know, at what pulse width you would start to do damage. This is a prediction of the, in Q space, of the intensity that you would see in the diffraction. So these are the diffraction spots, and you see as you go to wider and wider pulses, you start to lose intensity at large Q or smaller distances, so your resolution starts to go to hell. And then, because we had such a flexible machine, we're able actually to take data 10 femtoseconds, 70 femtoseconds, 200 femtoseconds. And what we see is that up until roughly 70 femtoseconds, even out to, you know, reasonable Q, this is again 1.8 kilovolt data, so we're not going to get super high resolution here, but we're not seeing degradation. But as you go to the wide pulse at 200 femtoseconds, you are starting to see damage in the crystalline structure. Okay. Yes. I think we can turn the light back on because I think everything else is going to be easier to see. Okay, so that was using a known sample, photosystem 1, a crystal that had been taken some people 10 years to grow it large enough to determine its structure at a synchrotron, but its structure had been determined. We used that as our fruit fly, if you will, to see if this technique, probe before destroy, could work at the LCLS. And then we set out and said, okay, let's see if we can solve a structure at the LCLS that no one has solved before at a synchrotron, because they weren't able to grow a big enough crystal. To do this, we wanted to go to the hard X-rays. We wanted to get high, good resolution, so we went up to the 9 kilovolts, 1.2 angstrom. And there's a end station specifically built in one of the hutches to do this. It's called the CXI end station. Any user with a sample can come and bring their sample and use this setup and get their structure out. Whereas the first experiments, the entire German group and their entire chamber had to come in order to get that experiment to work. And there's a pixel array detector that was developed at Cornell, Saul Gruner's group, and used is the CCD detector for this. Here is the geometry has changed a little in the CXI. We now have a vertical jet. By the way, I have to say I go down to the end stations fairly frequently because it's really exciting on the weekend when the user groups are running and see what's going on. And The X-ray laser is running all the time. It's got a 95% uptime. These damn jets clog. And the biggest loss of beam time for these experiments has been these microjets, and these nanocrystals tend to clog the jets. And so it's a very active, ongoing area of research to solve that problem. Anyway, here's the detector, the jet. The X-ray laser comes in from the right in this picture. This is a diffraction pattern from the cathepsin B, published in Science. That's not really so exciting. This is what it looks like when you combine a couple 100,000 images. And this was the first structure that was extracted at the X-ray laser, determined at the X-ray laser, that had not been previously determined. And it's actually a fairly important structure. It's key to the, it's an enzyme key to the survival of the parasite responsible for African sleeping sickness. You can figure out how to keep that parasite from surviving. You will actually do a great deal towards eliminating, which is what is a pretty terrible disease. So this was actually a really big deal last year. It made Science magazines. We didn't get breakthrough of the year. That was the discovery of the Higgs. That's pretty hard to compete with. But we were one of the 9 runners-up with this, and we're very excited about it. Probe before destroy works. It's actually already turning into an industry. The biologists have gotten quite excited about this, and they are starting to line up to bring in their samples to see if we can use this technique. Not every sample works. Not every sample diffracts in these nanocrystals, but it's very dynamic, very exciting. But I showed you that movie of the horse. We really want to do dynamics. I'm still actually just doing static structure, but with different samples. What about dynamics? And so can we make, photosynthesis the movie? All right, so you all know what photosynthesis is. You take energy from the sun and carbon dioxide and water from the ground, and you turn that into the waste product oxygen and sugars for the plant, which is the fuel for the plant. So it's sunlight into fuel is the basic process of photosynthesis. And of course, it's all around us. It's actually quite a complex process. This is actually the photosystem 1 membrane protein, which I just showed you diffraction patterns of. And I'm going to be talking about photosystem 2. Photosystem 2, we know its static structure has been determined, but there's a process. I'll give you an illustration, just a cartoon of it, called the Koch cycle, which is how the photosystem 2 membrane protein splits water into the oxygen, which is going to be the waste product of photosynthesis, and the hydrogens, which are going to be key to making the fuel for the plant. And we don't actually really know how photosystem 2 does it. It's a 5-step process where you absorb a photon. So you start out, actually, this is the dark state. This is what you get if you had photosystem 2 in a dark room. It's in the S1 state. You absorb a photon, you go to S2. You absorb a photon, you go to S3. You absorb a photon, you go to S4. You release the oxygen. The water's been split, and then you get back to S0, which is the most reduced state of the photosystem 2. And in particular, the point at which the water is split and the oxygen is released, S3, S4, we don't know what's going on. So the idea here was actually to make nanocrystals of the photosystem 2, determine the structure in the dark state, and then before, so that's one experiment. Experiment number 2 is take nanocrystals of photosystem 2, illuminate them with a laser just before you determine the structure, and now you get the S2 state. Ultimately, give it 2 photons, get the S3 state, 3 photons, get the S4 state. Now, there are 2 teams who are doing these experiments at the LCLS. They are fiercely competing with each other. Team 1 has published 3 papers, but with not such great resolution, sort of 4.5 angstrom resolution. You really want to get below 3 angstrom resolution. Team 2 has a paper they're writing, but nobody knows what's in it. So I can't even tell you what the gossip is because they're competing so fiercely that they're not even giving any hints. But Team 1 has determined S1 at the LCLS and S2 at the LCLS. We really think the action starts to happen and the configurational changes in photosystem 2 happen at S3 and S4. So the really exciting stuff hasn't been seen yet, but this is what the little nanocrystals of photosystem 2 look like. Big surprise, they're green. And this is what a diffraction pattern looks like, and you can see spots out to about 5 angstroms, which tells you the resolution is not going to be great. You'd really, as I say, like to get this more diffraction out to wider angles to get the resolution, a higher resolution. And these are two kind of complex plots. Let's look at this one first. This is just, it's really the data of these meshes, and all the yellow and the pink stuff is put on top of the meshes. The meshes are the electron density distributions, and this basically shows that they are able to, for the dark S1 state, determine the structure consistent with what has been known about the structure of photosystem 2. And then this is the, in some ways, more interesting plot, which is it's a difference plot between the S2 illuminated state and the S1 dark state. The actual data, again, is the meshes. Everything else is a cartoon overlaid on the meshes. What the difference plot is telling you, these are not very significant differences. I think green is plus and red is minus in the structure S2 minus S1. Basically, what this says is the structure hasn't changed going from S2 to S1, which is actually what was expected. And this is being shown around the manganese cluster, which is where the action is happening. So, bottom line is, stay tuned. Right now, we've been able to look at S1 and S2, and there isn't a big difference. So what have we learned? Well, we've learned probe before destroy works, and this nanocrystallography or serial femtosecond crystallography, it goes by both names. That's the first killer application of the X-ray laser. Still static structure, but it will allow us to access structures of things that were previously inaccessible. Chemical dynamics is being studied. There have been some, this is a very narrow slice of what's going on right now. There's some very beautiful experiments looking at model systems where you look at catalysis on like CO desorbed from a ruthenium surface, and they're seeing new states that indicate what happens in this desorption process from a catalytic surface. A lot of material science applications. So the dynamics is definitely coming and being worked on. Next steps in this diffraction businesses and the imaging businesses, there's a lot of question. Can we image a single particle? So far we've been taking advantage of Bragg's law and using these nanocrystals. You lose that when you go to a single particle. At that point, you have no way of dealing with the heterogeneity, if you will, of one sample relative to the next one and how you orient them. Can that problem be solved? Actually, Weidelser is one of the pioneers of this field. He believes it can be. But that will determine, whether we can image a single particle, whether it's a single molecule, which is that's the dream. Or there's also some very interesting work going on about, can you actually image at obviously lower resolution a virus or a single cell? Okay. Lots to come. LCLS has been a success of our wildest dreams. The laboratories, the people who built it, our sponsors, the Department of Energy. And every now and again, when everything goes well, you actually get rewarded. And the reward here is, first, the scientific demand is so great, we're turning down 4 proposals for every one we allow time on the beam. And that's bad, because science is not happening as fast as it could be happening at the LCLS, because there's just not enough beam time. And if we were really smart and knew that we wanted to do a particular kind of science, we could give all the beam time to that particular kind of science. But this machine enables many fields of science, and none of us is smart enough to know which ones are actually going to be the most exciting. And so increasing the capacity of the X-ray laser is critical. We are, as I'll show in the next slide, already doubling the capacity by now taking the middle section of the LINAC and building another 2 more undulators and more experimental halls. There's other things we want to do. We'd like to extend the spectral range. We would like to go to both lower energies, well below carbon cage, and to harder energies for better penetration. Ultra short pulses below a femtosecond would be great. Polarization would be great. That lets you separate spin and charge effects. And there's no reason we can't polarize the X-ray laser beam, so that's being worked on. Work on the seeding. We can seed now at the hard end, the 9 kilovolt end. The self-seeding technique I told you about works for hard X-rays. We're developing a technique to self-seed at soft X-rays because people want the control of the pulses down there as well, and then capacity. This is what LCLS2 will look like. So this is LCLS1. You can just see there's 280. This is the third of the LINAC we're using, the drift. The undulators are under this hill, and then the near haul and the far haul there. A new injector is being built. This is foreshortened, but so this here is 2 kilometers. This is 1 kilometer. This is the 2nd kilometer. Oh, yes, there's that 3rd kilometer of unused LINAC. You can guess what we've got our eye on, which will be yet a 3rd extension. So that will be the sectors of the 30 sectors of the LINAC. We're using 21 to 30 for LCLS1. LCLS2 will use sectors 10 to 20. Then we will have a dog leg and a bypass, and there will be a new undulator tunnel under the hill and a new X-ray hall. Actually, this shows it's going to probably be farther. Actually, maybe this has gone back and forth. I think actually this is correct, the new underground hall there. And so the near term is really exciting. We're expanding LCLS. There are new facilities turning on. The Japanese have turned on a X-ray free electron laser at called SACLA at Spring 8. It's not got quite as much per pulse energy as LCLS, and it's only operating at 60 hertz. They have some problems to get the rep rate up higher, but they're starting to do some really beautiful science, and we really welcome them because, as I say, we're limited in the science we're doing because there's just not enough access to the beam. The Germans are building a very large facility, the XFEL, which will have a very high rep rate, higher than LCLS into the tens of kilohertz, and that will be great. There's a Swiss X-ray free electron laser being built. There's a Korean X-ray free electron laser being built, and we're already talking about a next generation light source in the U.S. past LCLS2. It's really a growth area. It's a new scientific frontier that's been opened. This opportunity now for dynamics at the atomic scale, not only seeing where the atoms are and where the electrons are, but what are they doing on time scales that they're actually doing interesting stuff. And I think all of us who are involved, I mean, I've given you a few examples of science. I could give you more examples of science, but I think all of us involved feel that the biggest surprises are really yet to come. We don't know yet what the full extent of what this tool will give us in the future. So with that, I will end. Thank you very much. Yes. Okay, so self-seeding affects the pulse duration in the following sense. We can only do it right now with the very short pulses, okay? Because we just don't have we can't separate. So it's sort of fixed at the 10, 15 femtosecond pulse width. What is the knob that we use to control the pulse duration is actually the charge of the electron bunch. Okay, so the mode of the very short pulses is called the low charge mode because we actually dial down right at the source the number of electrons in the bunch, and then we can just make a smaller compact bunch, and that allows us to just limit it to 1 or 2 coherent spikes. Yeah. Oh. Absolutely. Yeah. We just need the right kind of undulator at the end of the electron LINAC. I think it was Claudio, must have been, that was his seminal contribution, Claudio Pellegrini, to recognize that that would happen. It's extensively modeled, and there are many problems that were, I didn't go into the details, but if you do the modeling, then there are some danger zones you can get into with the electron bunch that you have to stay out of. Sometimes you actually can't let it go as far in microbunching as it might want to go. But it's well understood by simulation. And in fact, one of the triumphs, I would say, of the LCLS has been the work of Zhirong Wang and others who have been able to simulate the machine to the point that we make many of the innovations, short pulses, self-seeding, were simulated and predicted and then delivered in machine development time. An intuitive picture of why the bunching would occur. Well, I mean, it's the interaction of the electromagnetic field with the bunches, which are being driven by the undulator at a particular frequency. Something more intuitive than that. It's self-amplified spontaneous emission. Stimulated. I think we're getting into semantics. The way, so I'm not in accelerator physics, but the way the accelerators will insist is that they do not need, they can do this with electrodynamics. They don't need to invoke Einstein A and B coefficients, right? They don't need to invoke quantum mechanics. You can't do that. Well, yeah, okay, you're right. You can do the same with atoms. Mm-hmm. Right. Okay. So they're not quite enough for that. A couple of things, though, that you bring up, all of which are really good points. What we actually use the extra undulators for, first, it allows us to take an undulator out and put in the self-seeding. And then what we found is after the exponential gain, there's actually a linear gain regime where if we taper the remaining undulators, we can actually eke out a little more gain. Again, something predicted in simulation works in real life. So that's what we've been using the extra undulators for. To address this, we've now actually developed a large offset monochromator to be able to, so because some experiments want a very narrow bandwidth, some experiments just want lots of X-rays. And so with clever scheduling and the use of a large offset monochromator, you can actually split the beam and send part of it to one experiment and the rest of it to another experiment. And some experiments, you can let it go through one experiment and then just go on to the next experiments because they don't actually disrupt the beam. So we're aggressively exploring those. Now, what you would get with your scheme was I could actually have the second undulator at a different color. Okay, which would be terrific. And that we can't do. We are, though, the accelerator physicists are really, this has been an accelerator physicist's dream, this machine, okay? And they keep coming up with these clever ideas. One of the things, the latest thing that's really sweet is that they can actually, so that little Russian crystal we put in has more reflection planes than just the one that I illustrated there. You can use that to get two colors simultaneously out of the, well, you take two notches, you get two rings, and you can actually have two color operations simultaneously, which is very good for some experiments. They've also got something called the spotted spoiler where they can take and give people two very closely spaced in time correlated pulses. So they have, there's just enormous flexibility with this machine. Yeah. No, they are not. No, they are not. And I've actually asked the question, is there you could get two coherently related colors if somebody said what the experiment was they wanted to do with it. That's not out of the range of possibility. They have to be pretty close in frequency. But you, That's right. Well, so we haven't done that in the only non-crystalline samples we've looked at in the same way as we use diffract before destroy have been viruses. So we have looked at viruses. If for something like photosynthesis, you wouldn't get enough signal. Right now, we need Bragg's law to help us get enough signal to be able to see those diffraction spots and get a structure.
I'm curious, you mentioned that you had laser after 3 hours.
Yes.
So how many underlay sections did you have in place, or will you use it at that point?
So we were prepared to put all 30 on. And what you're asking is, at what point did we see it start to laze? I think they started seeing intense radiation after about 10 undulators on the beam. I mean, I can actually, well, I showed that game plot, and you can, at the bottom of the game plot, they started to see stuff. It was real exciting. Yeah. Sure. Yeah. Yeah. Yes. That's right. Drop a little crystal in, I image it, I get a diffraction pattern, that crystal's gone. Next one drops in. No. I don't have control over the orientation. It's a really good question. So right now, we get enough information from each diffraction image to be able to orient it relative to all the other ones, because those spots are so damn clean. But there's money to be made, figuratively speaking, if we could orient samples and remove a couple of degrees of freedom from the problem. That would be the path, in my view, to being able to do single molecule imaging without having Bragg's law. If I don't have Bragg to help me orient them, I need something else. And so there's some very active R&D programs on how to deliver samples in an oriented way. You can imagine taking advantage of a magnetic moment or electrostatics or something. A lot of R&D going on that. Thank you.